All right, class, welcome. So this is a video for my not so reading kind of verbal people, well, verbal, but not people who enjoy reading. So this week, the lecture was kind of a mess, and I'm so glad that I figured out how badly it was falling apart because I've gone back through and I've created this packet. So what this recording will be is taking people through the packet who maybe um, aren't um, going to be able to read the packet and really get it and need somebody to sort of visually take them through it. Or you're welcome to, read the packet and follow along. That's a good thing. So we're going to talk about phase today. So this is the old Star Wars light weapon. We're going to talk a lot about phase. And it was called the phaser. This is a phaser rifle. And what I say in the thing here is Kirk shooting a phaser at an enemy. It's not really strictly a phaser, it's a phaser cannon. We're not going to cover lasers until Unit 4, which is coming up. But to give you a hint, they have something to do with the phase of light that comes out of them, and that's why this laser-looking weapon is called a phaser. So I'm not going to just read you this whole packet, I promise. So even if you're not going to read the packet in depth, I am continuing to do the freshman MIT core and other classes, and so I list those. There's a new one that got added, which is 6001, 6002. You can actually take these on edX for free. Some of these other ones have been divided up on edX. Most of them you can get for free. You can get them on OpenCourseWare if you want to take a look at them. But I just put little notes, and they're usually in green. All right, this is going to say transverse waves in one dimension. Is it really one-dimensional? Because it's got like this up-down. We're going to be mostly talking about this wave on a string thing. And so am I really talking about one dimension? I mean, strictly one dimension would just be along the line, like the number line is one dimension. But this has an up-downness to it. Well, just bear with me, and we're going to call this a one-dimensional wave for this time. The next packet that I'll give out next week, we're going to talk about waves spreading out on like the surface of a pond, and that's much more a two-dimensional wave. So we will talk about more two-dimensional waves next time. So don't let the one dimension kind of fool you. It's just to distinguish it from next week. Okay, before we get started, there is a way to do this in real life, and that is there are people on the web, and I'm going to put one video on our weekly page that is a woman, physics teacher, AP physics teacher, who was able to show resonance on a string. So she has some students, I think a student who's waving a spring, a long spring up and down, and she shows resonance. By the end of this packet, you will be doing resonance. So don't worry if you don't know what that is yet. So I'm probably just going to put that one up. Most of the videos online have a student or a teacher, and they're standing and they're going up and down. And in the packet, I reference it as if it's that way. If you want to do this at home and you want to see the wave on a string working, and you can actually see the reflection happening, if you get somebody to hold it still on the other one, what you have to do is imagine all this beige area here, this tan area, is the floor, and you have to lay the wave on the floor, and instead of going up and down, you're going side to side. We're going to use the pulse a lot because the pulse seemed to be the place where the lights kind of turned on at the end of lecture. If you're going to do the pulse wave, just make sure that you have a wall down here, that there's a wall to prevent it from going. See, the pulse wave doesn't go down. Well, it does go down. Ooh, maybe I should change that. Maybe I should change that. All right, I'll change that in my instructions. Yeah, because you won't be able to see the reflection if you don't do it that way. I guess you'll just have to manually restrain yourself from, as long as you manually restrain yourself from going low, it should work. All right, so I'll have to change that in the packet. All right, as far as what material to make it out of, you want something smooth that will move over the floor if you're going to do this in real life. I recommend that you just use the simulator, but if you, it's really good to, some people really, I do very well if I do things in real life. I've seen it work really well with one of these, but it was a really long one of these, and those can be expensive. So if you are fascinated by this, you want to go to the store and get something that will work, and you want to go to Home Depot. They do have chain, you would need a smaller amount of chain because the chain will move back really easily. But make sure it's a really light chain that will move really well. Or you can get a longer piece of rope, but get it smooth, probably like a synthetic rope, not a natural rope, that will move across your floor really smoothly so that there's no friction across the floor. That's just if you want to do it in real life. Most of what we're going to talk about today is a simulator. Okay, so the main takeaways today are this word phase. I don't expect you to know what phase is right now, but this word phase, what I want you to know about it is phase has something to do with where you are in the shape of the wave. We are going to use a math trick, not Max Planck's math trick, but a different math trick. And this math trick, which you will figure out if you do the math path, will allow us to call this the phase angle. This place in the wave, the phase angle, because the where I am in this wave angle was too long. Waves can add and subtract from each other. That's another thing that you should know leaving here. We're going to use that waves can add and subtract from each other when we prove that light is both particle and wave. A wave moves because when a particle in the medium is disturbed, it disturbs other particles. Just pretend like light has a medium for a while. But when a particle in the medium is disturbed, it disturbs other particles. When waves are reflected, all the energy is sent right back, but it's out of phase. Again, we haven't really covered what the phase thing is, but it has something to do with where you are in the wave shape. And we're going to look at resonance. So those are the big takeaways. And I have here in orange, when you get done with this packet, come back to this section and say, did you get all this stuff? So if you're just doing the video, when you're done with this video, just get the packet and look at it either online or, you might want to print it out. I think it's 18 pages long. It's really long. And just ask yourself and refer back to it. Did I get this stuff? Did I at least understand this stuff? And by understand, just these topics. There's more depth to go into all of this stuff. But a lot of it's going to have to wait for 8:03. All right. So we used a pulse wave in class. And that's when people really started to get stuff. All right, I'm going to always turn my damping down. Well, until we get to resonance, I'm going to keep turning my damping down. All right. And let's talk about the first topic. There is a certain shape to our wave. It has a wave front. This is the very first part of the wave. It has a peak, and then it has the end of the wave. This is called the end of the wave pulse with a pulsed wave. Okay, so in class we talked about Zara sending a pulse wave to Nick. So Nick is going to hold this green bead very still. He's not going to let it go up and down. That's why they show this as like a clamp. And Zara is going to press this button. It's going to go up very quickly and down. A pulse wave isn't going to look that different in this simulation from when they do the oscillation. So if you look at how just watch how this goes up and down. Oh, sorry, let me restart. Just looking at the up-downness of it, that doesn't look that different from what this is doing. This is going up and down. But in what they're trying to simulate is very different. It's an instantaneous, almost instantaneous thing of electricity that goes really abruptly, right? So that's why they're showing it as a triangle going down there, much more than a smooth wavy waveness. All right. Okay, but there's a certain shape to our pulse wave. This isn't the same as, so I've already used the word oscillation today, and maybe, so there's oscillate, and you need to know the definition of oscillate. Oscillate, lots of things oscillate in lots of different ways. Most of the waves we're going to talk about do this oscillation thing. A pulse goes up from equilibrium, down to equilibrium. That's what a pulse does. Oscillation means you go above and below equilibrium. Equilibrium line is this orange line through the middle. All right, I'm going to stop this first one so you can take a break. This is a good way to do it. You can take a break, and I will return to you in a second session.